lecture. So when we last discussed acid-base reactions, our goal was to predict the position of an equilibrium for a range of acid-base reactions. The places where this practically comes up is when you're trying to work up a reaction or where you're trying to generate a desired conjugate base product or conjugate acid product. So for example, when you want to terminate a reaction and work up a reaction, your goal is to react any remaining excess acids or bases in solution at the end of the reaction. And so for example, suppose you have the following anion. Would it be suitable to protonate the following anion with water? So to answer this question, we're going to need to look at our pKa values. So the pKa of water. So what is the approximate pKa of water? Well, if we go to our pKa table, we have a pKa of around 14. Okay, let's figure out the pKa of this proton. Let's try to figure out the pKa of that proton right there. So let's go to our pKa table once again. And a malonate has a pKa of roughly around 13. Okay. The pKa will probably be a little bit lower as a malonate has 2 esters while this has a ketone. So comparing our pKa values, is this equilibrium reactant or product favored? Looking at this equilibrium, is it reactant or product favored? What does everyone think when we compare our pKa values? This reaction is reactant favored. Exactly right. So this reaction, as drawn, is reactant favored. So if you tried to quench this anion with water, you would not end up with complete conversion to the products. You'd end up with a substantial amount of reactants remaining. So it's really important to think about pKa values in the context of experimental procedures because it determines what you use to quench certain reactions. So you always want to think whether or not your reagents are actually accomplishing their intended purpose. Does this example make sense? So here's another example of a somewhat common mistake or issue. So lithium diisopropyl amine is a common base used in organic reactions. If you deprotonate it, you generate LDA, lithium diisopropylamide. You commonly generate LDA using N-butyllithium from diisopropylamine. This is our good old friend, diisopropylamine. We commonly generate lithium diisopropylamide from N-butyllithium. And this reaction is relatively product favored. So let's look at a theoretical example where suppose that you've run out of N-butyllithium and you still want to make LDA and you try to break out the following reagent to make LDA. Would this work? Would this modification of the experiment procedure work? Well, I'm going to need your help on this one. What do we need to figure out whether this reaction is functional, whether this reaction is reactant or product favored? What values do we need to look up? What values do we need to figure out in order to predict?
PK.
Yep. And what pK values do we need to find? What pK values should I fill in to help me solve this problem? So if I'm making a list of pKa values, what pKa values should I write down? For the acids, okay. So what is the pKa of diisopropylamine? What is the pKa roughly? Looking at our table, what is the pKa value of diisopropylamine? 9 to 11 is for the ammonium salt. So looking at our pKa table, what is the pKa of an amine? Not a protonated amine, just a normal amine. Would anyone like to volunteer? What is the pK of a normal amine? Roughly 35, right? Right here. Okay. So let's write that down. Okay. What about this acetylene? So what is the pK of an alkyne proton? What is the pK of acetylene roughly? 25. Okay. So is this reaction reactant or product favored? Is this reaction reactant or product favored? This reaction, as written, is reactant favored. Now, this is important because you may just think, oh, I changed the base. It shouldn't have a dramatic impact on my reaction. But as we can see, modification of our base can result in a switch from a product-favored reaction to a reactant-favored reaction. So again, I always encourage you to think deliberately about your choice of reagents. Do these examples make sense to everyone? These are some practical examples of modifying your reagents and modifying your procedures that can dramatically affect your experimental results. Whoops, one moment. So, one last factor that we need to consider is the idea of solvent choice and the leveling effect. So this primarily applies when we have protic solvents at play. So the leveling effect simply states the strongest base that can be present in a solution is the conjugate base of the solvent, and the strongest acid that can be present in the solution is the conjugate acid of the solvent. This is why we don't typically run many basic reactions in water, because if you have your organic base and you have water with a pK of around 14, if we compare that to the pK of the conjugate acid, you end up with a highly reactant favored process to generate hydroxide, which is the solvent conjugate base. Now, this also has its benefits and its drawbacks, where if you take, for example, sulfuric acid and you put it in water, so this acid with a pK about -7 compared to our conjugate acid pK of -1.7, the strongest acid that you can have in an aqueous solution, oops, one moment, the strongest acid that you can have in an aqueous solution is the solvent conjugate acid. So your choice of solvent creates a ceiling and floor for the maximum and minimum pKa values in solution. So the reason why this comes into play is you want to make sure your solvent has a higher pKa than the conjugate acid of any bases used in the reaction. This is where you can end up generating quite a hazardous reaction mixture if your solvent ends up participating in the chemical reaction. If the solvent is more acidic than the conjugate acid of your reagents, you will just end up deprotonating your solvent. So nitromethane is a nice and wonderful solvent to use. Nitromethane, shown here. I know it may seem like the solvent's just this tiny little thing that's put above the box. Why should I care about it? Well, would someone like to tell me what is the pKa of nitromethane? From our tables, what is the pKa of nitromethane? Just out of curiosity, what is it? Looking at our table, so going to our table, what is the pKa of nitromethane? So we don't see any nitro groups in this first table. Let's look around and let's see if we can find let's see. We've actually talked about the nitro groups before in an earlier example. And earlier in our notes, exactly right. The pKa is around 9 to 10. Perfect. Thank you for bringing that up. We actually talked about it in our discussion of inductive effects on, I think, roughly page 15 of notes. Yes, so this has a pKa of around 10, while your typical ester has a pKa of around 25. So then, if you have your base, and you have a ton of your solvent, which species is more acidic? Your reactant or your solvent? Which species is more acidic? Solvent. So the solvent is more acidic. And as a result, your reagent will end up reacting with your solvent. So the point of this example is to show you need to deliberately choose your solvent for your chemical reaction. Incorrect choice of solvent can result in undesired side reactions that can not only prevent your desired reaction from occurring, but it can also pose a safety hazard if these side reactions are exothermic. Does this example make sense to how solvent choice can directly impact whether your chemical reaction is successful? Does this make sense to everyone? Okay, so let's keep going now. And sometimes solvent reactivity is not necessarily a bad thing. Some reactions are run under equilibrating conditions where they generate a solution of the solvent and its conjugate base for reactions. So for example, sodium hydride with hydrogen having a pKa of around, let me look, hydrogen. Let me find hydrogen. Here we go, pKa of around 36, okay. We have our tert butoxide, which has a pKa of around 17. And we have this diketone, which if we compare to our malonate, should have a pK of substantially less than 13. The pKa is closer to 9 for this diketone. So as we can see in this reaction, first, our sodium hydride reacts with our solvent and we generate tert butoxide, and this is our base. This is the base that is used in our chemical reaction. So solvent reactivity can be leveraged for equilibrating reaction conditions. Does this make sense to everyone? So solvent reactivity is not necessarily a bad thing entirely. Does this idea make sense? Any questions so far? Okay, so let's talk about some common solvents. So solvents used under strongly basic conditions, these include tetrahydrofuran, otherwise known as THF, hexanes, benzene and toluene, and diethyl ether. These are the most common solvents that you'll see as part of conditions in your textbook. The following solvents pose issues under basic conditions. The following solvents pose issues: alcohols, amines, nitrile groups, nitro groups, any derivatives of acetone or ethyl acetate. All of these solvents have acidic protons that can potentially generate undesired side reactions. The chlorinated solvents are a little bit interesting in that you may not think these protons are particularly acidic, but if you go at it with a strong base, you could definitely start to react and decompose your solvent. So this just will help you when you're looking at chemical reactions to be familiar with the solvent and note that the solvent is not necessarily an innocent component of any reaction. Does this idea make sense? Any questions so far? Okay. So the last topic that we need to discuss is this idea of Lewis acids and Lewis bases. So a Lewis base is defined as a lone pair donor. So if it's able to donate a lone pair and donate electron density, it functions as a Lewis base. These include alcohols, ethers, aldehydes, ketones, and a range of other functional groups. A Lewis acid is a lone pair acceptor. Lewis acids typically contain an empty p orbital. These include metal cations such as magnesium 2+, as well as group 3A elements such as BF3 and aluminum chloride. So if we look at the structure of aluminum chloride, for example, it has an empty p orbital that it can use to accept a lone pair. Additionally, transition metal compounds such as titanium tetrachloride, iron 3 chloride, zinc chloride, and tin 4 chloride are Lewis acids. And organic compounds in general that undergo addition reactions with Lewis acids, that undergo addition reactions with Lewis bases are called electrophiles. And therefore, these organic compounds can function very similarly to Lewis acids. So an example of this would be a cationic carbon with an empty p orbital that can accept a lone pair's worth of electron density. Okay, so why are Lewis acids important? Why are Lewis acids important? Well, let's start, whoops, one moment. Apologize for the small amount of lag with OneNote. Give me 1 second. So let's do an example where we identify the Lewis acid and Lewis base, and we use arrow pushing notation to show the coordination of the Lewis acid to the Lewis base. So aluminum trichloride is commonly used as an activating agent to activate ketones and other functional groups for further reaction. So, which of these species is our Lewis acid? Which of these species has an empty and available p orbital? Which of these species can accept a lone pair? In the following reaction, what's our Lewis acid in the following reaction? The aluminum trichloride, yep, this is our Lewis acid. What is our Lewis base? What is our lone pair donor? What is our lone pair donor? So if aluminum trichloride, AlCl3, is our Lewis acid, what is our Lewis base? Well, then as a result, our ketone, which is acetone, is functioning as our Lewis base. So our Lewis base donates a lone pair, our Lewis acid accepts a lone pair, and we end up with the following adduct. And as we notice, our oxygen ends up building up a positive partial charge or even a positive formal charge. And as a result, we've activated our molecule for further chemical reaction. Does that make sense? Does this idea of Lewis acids and Lewis bases make sense? Okay, so let's look at a follow-up example. So I'd like everyone to take about 2 minutes. I'd like you to indicate the Lewis acid and Lewis base, and I'd like you to use arrow pushing notation to show coordination of the Lewis acid to the Lewis base. This is the first step in Lewis acid catalyzed epoxide opening or epoxide rearrangement reactions. So I'd like someone, if possible, to break out the annotate tool and try annotating their proposed solution. And we'll discuss this example in about 2 minutes. And don't be shy to share your responses. And at the bare minimum, I should see in the chat some indication of which molecule is our Lewis acid and which molecule is our Lewis base. And don't be shy to share your questions or responses in the chat or verbally. Okay, so we see an assignment for our Lewis base and Lewis acid. Now let's draw the arrow pushing notation to show the lone pair donating its electron density to our Lewis acid. So let's draw an arrow from our lone pair to the Lewis acid. Allow me to help. I greatly appreciate the identified response. And let me show you how to draw the arrow a little bit more explicitly to show the donation of electron density, but the idea presented looks great so far. So let's clear this and let's provide the instructor solution. So as the class is correctly identified, we have BF3 as our Lewis acid, while this epoxide will function as our Lewis base. The Lewis base donates a lone pair to our Lewis acid, and we generate the following adduct. This adduct can then react via a range of reactions as this epoxide is now activated. Does this idea of Lewis acids and Lewis bases make sense to everyone? Perfect. So this is a pretty cool application. This is our first example of a mechanism. So the Nazarov cyclization is a Lewis acid catalyzed cyclization of a divinyl ketone. So first, I'd like you to draw the coordination step of the Lewis acid, and I'd like you to draw the two major resonance structures for the cationic intermediate. So you're not quite asked to draw the full mechanism yet, but I'd like you to explain and show me the major cationic intermediate in this reaction. So let's take about 2 to 3 minutes, and I'll give you plenty of space down below for you to draw the adduct and one major resonance structure that can help us understand the reactivity observed during the Nazarov cyclization. So ideally, I'd like one or more students to try drawing out some structures and drawing out some potential resonance structures of the cationic intermediate that is produced over the course of this reaction. So let's try to get some proposed mechanisms and intermediates drawn for the following reaction, and then we'll discuss in about another 2 to 3 minutes. And if you have any questions or a proposed solution for this problem, don't be shy to share it in the chat or verbally. And we'll discuss this example in about another 1 minute to a minute and a half. And remember, the annotate tool is accessible from the tab titled Meeting Options as part of the Zoom call. Okay, so let's first talk about the first coordination step. So our Lewis base reacts with our Lewis acid. We in turn generate our adduct. And shuffling our electron density around, we can draw an arrow pushing structure that showcases that we have a lot of cationic character built up on our adjacent carbon atoms. And this is really what allows the Nazarov cyclization to work, because you're able to get an attack followed by an elimination event. So this is the kind of resonance structure I was looking for. The mechanism part that I'm showing you now is just for your personal gratification, so you can understand and sort of appreciate how these different named reactions function. We have a lot of the tools at our disposal already to rationalize and understand these named reactions. So does this example make sense? And does everyone see how Lewis acids can be utilized to activate molecules for desired reactions, in this case for a Nazarov cyclization? Does this make sense to everyone? The role of Lewis acids and how Lewis acidic and Lewis basic character of molecules is directly invoked in writing reasonable reaction mechanisms. Does this make sense to everyone? I always like to include pretty practical examples of named reactions when we talk about different topics in this course, as you'll be seeing these named reactions again in later organic courses. Any questions before we close out this section? So we've reached the end of chapter 2 and we're just about ready to get started with chapter 3.